the second part of section 2.6 deals with something very exciting. How do we now tackle the challenge of finding limits of trigonometric expressions? So if you look at the first limit that we have right here, we're asking you, what is the limit as x approaches 0 of sine x over x? What is that limit? Now, I can give you a actually very beautiful geometric proof, but it will take a while. However, for those of you who are truly curious about mathematical proofs, please go to the book, and you're going to see that the author there, Rogowski, will go ahead and show you a very nice geometric proof of the limit of sine x over x as x goes to 0. Now, just because I'm saying nice, it doesn't mean that it's super easy. If it was super easy, I would go ahead and do it here in the video. It wouldn't cost me anything. But it is lengthy, and so some elements are a little bit heavy in geometry. And because the proof going behind the scenes is not something that you need for the exam, I'm going to go ahead and skip that proof. But it is there, and it's super nice for those of you who are really eager to go behind the scenes of mathematical results. But if not, just knowing the actual result is good enough for this class. So what is this limit? I'm going to go ahead though, and instead of giving you the answer, I am going to give you a graphical reasoning behind the answer. I will not do the proof, but I'm going to be able to convince you graphically why this limit is equal to a specific number, because it is actually equal to a number. Why? What is that number? Look over here. I have the sinusoid. The red graph is the sine graph. I just didn't finish the oscillation, but then sine is going to go up and down, and then it continues going up and down, up and down. And the same thing here on the left. I just did not continue because I am focusing on the limit as x approaches 0. So in this neighborhood right here. And then I am sketching the line y equals x. We are all super familiar with the line y equals x. What I want you to notice is that around 0, look at the graph, around 0, let's say from here to here, the sine graph, it's pretty much linear. Look at this, so linear. In fact, I'm going to go ahead and trace that linear part. So from here to here, follow the green marker. See how linear that part of the graph is. In fact, you can't even tell the graphs apart. Now, the sinusoid deviates from being linear, right? After a while, it keeps doing something like this. It keeps going up and down. But what is really fascinating is that in a very small neighborhood, let's say from here to here, in this tiny neighborhood around 0, the sine graph, it's practically linear. It identifies, it matches perfectly with the line y equals x. So then that means that this line y equals x is a beautiful approximation for the sine graph around 0. But please, I keep emphasizing around 0, because as soon as you move away sufficiently from 0, I'm going to continue here, the line y equals x continues all the way up, and notice how it moves farther and farther away from the sinusoid. But again, around 0, y equals to x is pretty much identical to the sine of x. So with that in mind, we can do the following. The limit as x approaches 0 of sine x over x, will be approximately equal to the limit as x approaches 0. And now what I am going to do here is I am going to replace sine x with x. Because remember, around 0, sine x and x are identical. So I can do a substitution and I can say x on top and x below. And whenever we do that, the x's divide each other out and you end up getting 1. And this is the fascinating result here, that this limit right here, the limit as x goes to 0 of sine x over x, is always equals to 1. In fact, in the proof, if you look at the proof, it is not an approximation, it is actually equality. So I am going to write over here exactly that result, that the limit as x approaches 0 of sine x over x is equal to 1. And this is such a major result in calculus that I really would like to ask you never ever to forget that. This will pop pretty much in about, I think, 3 or 4 chapters in this entire year. So it's something that is going to keep happening and happening and happening. But in general, it's a good advice to try to never forget it. The limit as x approaches 0. Please note that x has to be approaching 0 because it is only around 0 that the line identifies with the sinusoid, that the line pretty much is identical to the sinusoid. It's in a very small neighborhood around 0. So around 0, the limit of sine x over x is equal to 1. Let's go ahead and do this problem. They're asking us to prove that the limit as x goes to 0 of cosine x minus 1 over x is equal to 0. This is a result that you can try to memorize after we prove it, because it is going to pop in the homework assignment and you don't have to be showing this every single time. I'm going to show you how to show that the left side is equal to the right side. But once I show you that process, you are more than welcome to memorize it or remember it and just apply it whenever it pops up. You don't have to keep showing that this is the case every single time. Now, in order to prove a result, you must remember from your work in trigonometry last year that whenever you have to prove an identity, this was last year, you had to pick one side, do some algebra to that side, and then hopefully obtain the other side. In this case, because the left side is the one that seems very involved, I'm going to start with the left side. I'll try to do some work on it, and then hopefully I will end with the right side. So let's go ahead and do that. So starting with the left side, we have the limit as x approaches 0 of the cosine of x minus 1 divided by x. Now, you know that we're going to do some algebra. So from your experience of trigonometric identities, what do you feel we have to do? Think about it. Something is screaming here for a particular action. What is that action? Let's have a few seconds. What would you do? What do you think we need to do? I am hoping that you're thinking multiplying top and bottom by the conjugate of the numerator. Look at the numerator. I have a difference. So if I multiply top and bottom by cosine of x plus 1 over the cosine of x, hopefully I will be able to keep doing some work here. When we do that, we're going to have the limit as x approaches 0, And if you remember, whenever you multiply conjugates, you get a difference of squares. So this will be cosine squared x minus 1 divided by x times the cosine of x plus 1. What I want you to remember here is the Pythagorean identity. We know that sine squared x is equal to 1 minus cosine squared x. I practically have this here. The only thing is that I'm going to have to put a negative in front of sine squared so that I get this here and this here. Everything switched. So doing that, we are going to have that this is equal to the limit as x approaches 0 of negative sine squared x, all this divided by x times cosine of x plus 1. So how do we continue? And the way that we're going to continue is by separating some of these components out. We're not changing the expression. We are just going to reorganize this expression right here. So let me show you how to do that. I want you to pay careful attention here. Just reorganizing these factors. So what I am thinking, since I have sine squared x, I am going to rewrite this as sine x times sine x. Now, this negative right here, I don't need, so I'm going to go ahead and push it in front over here of the, right here, in front of the limit sign. So I'm going to do that right here, negative. I am going to rewrite this as sine x times sine x divided by x times cosine of x plus 1, right? Doesn't seem complicated. In my next step, I'm going to do another separation. These guys are going to be completely by themselves, and these guys are going to be by themselves as well. This is what I mean. I am going to have minus, and then the limit as x approaches 0 of sine x divided by x. Now look at this. I'm going to go back to the previous step. Here I can think of this as a factor or a function, and this as another function. And both of these limits exist. In this case over here, as x approaches 0, cosine x plus 1 is 2. So the limit of this function exists, and the limit of this function exists. So I will write this as two separate limits. This will be the limit as x approaches 0 of sine x divided by cosine of x plus 1. Again, cosine of x plus 1 is not going to be 0, it's going to be 2. And sine is continuous at 0. So this limit must exist. And this limit right here, the limit as x goes to 0 of sine x over x, I'm hoping that you remember from the previous discussion, this limit is equal to 1. So this is why we can use the properties of limits, the properties from section 2.3, where we can apply the limit to the first function, the limit to the second function. I'm thinking of this as, let's say, a function f of x, and this one a function g of x, something like that. If you want to think of it in terms of functions, it doesn't hurt. And remember, this limit that was this negative sign that was outside remains outside. So in a sense, I have not changed the expression. I just reorganized the, several components, and I apply the limit to those two factors separately. And then I know that this limit right here is equal to 1 by the previous discussion. Remember, I asked you to always remember that the limit as x approaches 0 of sine x over x is equal to 1. So that's going to be equal to 1 over here. And then in the second expression right here, because sine x over cosine x plus 1 is continuous, I can do a straight substitution of 0. So I'm going to have sine of 0 over the cosine of 0 plus 1. That's going to be equal to negative 1 times 0 over 1 plus 1, which is 2, and that is going to be equal to 0, because anything times 0 is 0. So then this is how we show that the limit as x approaches 0 of cosine x minus 1 over x is always equal to 0. As I said, you are always, from now on, you are welcome to immediately claim this. You can memorize it. If you don't memorize it and you need to use it, and let's say you don't remember that it's equal to 0, now you know how to derive it. But it is a lot of work. So the advice is try to memorize it. Example 2 is asking us to evaluate the following limits. And the very first one, part A, is the limit as x goes to 0 of sine of 5x over 3x. Now, before I start trying to evaluate the limit, I just want you to remember the very special result, the one that we started this video with. We started talking about, or we found out, that the limit as u approaches 0 of sine of u over u is equal to 1. I decided to change that variable here on purpose because we often get too comfortable with x, because that's all that we tend to use, x and x and x, and I don't want to give you the wrong impression here. And sometimes in the homework assignment, the author is going to be playing with variables. So even in this example, you're going to see in part B, I deviated from x again. I used h, and in part C, I'm going to be using t. So u is a dummy variable. It's just the same thing as putting an x in there. The limit as u goes to 0 of sine u over u is equal to 1. Another thing that I want to inform you of is that if we have the limit as u goes to 0, and now we consider the reciprocal of sine u over u, if you have u over the sine of u, the answer is the same. This limit is equal to 1. And I know that this will pop in the homework assignment, and I don't want you to be confused about that. So the limit is still going to be equal to 1. What is important is for you to be approaching 0. Must approach 0, because only around 0 is where sine and the line y equals x meet each other. All right, so with that in mind, why don't we start? When I look at this problem right here, I'm thinking, my goodness, I wish that I can use this result. I have sine, I have x, but what's really bugging me here is 5x. I just don't have x inside of sine. I have 5x. So then, what do I do with this 5? Well, I cannot just erase it. I cannot just bring it out. I'm hoping that your understanding of trigonometry is pretty solid by now. That you know that if 5 appears inside of sine, it stays there. So there's nothing that I can do about 5x. So what we are going to do is the following. I'm going to take this 3, this coefficient, and I'm going to bring it in front of the limit for now. So I'm going to have 1/3 the limit as x goes to 0 of sine of 5x divided by x. Again, I haven't changed my expression. I just took 3 and I brought it in front of the limit notation. Then let me look at what I have over here. this looks a lot like my result here. But again, that 5 is bugging me. So I'm thinking the following. Well, what is wrong if I decide to multiply top and bottom by 5? Is there any harm in that? If I do that, the benefit now is that if you notice, these two here can be combined. So what I have is the following here. I'm going to have 1/3 the limit as x goes to 0 of sine of 5x divided by 5x. And the 5 in the numerator, I actually don't need there, so it can come and join the 1/3. So I'm going to write over here times 5 in front of the limit. Now, what is really nice about this is that now this expression matches this over here. Now I have sine of 5x over 5x. This is exactly like having sine of u over u. You can think of 5x right here as being u, and this 5x right here as being u as well. So now I have a match inside of sine and a match in the denominator. So there's only one slight modification that I have to make, and it has to be right here. You know, this is too messy. Let me rewrite it. So I have now 5/3 in front of sine. I have the limit as x approaches 0, and I now have sine of 5x divided by 5x. So can I claim that this limit is equal to 1? And the answer is almost. We're almost there. We just have to make one more modification. That for us to claim that this limit, the limit as of sine u over u is equal to 1, look at this. What we really need to have is the limit as u approaches 0. U has to approach 0. And I'm going to take you right here on the left. X is not matching with 5x. I have that x approaches 0, but I really need to have 5x. Everything has to match. Let's go back over here. U inside of sine, u under sine, and u has to approach 0. U, u, u. U, u, and u. Here I have 5x, 5x, but I just have x. So there's a slight inconsistency, and I have to fix that. So what I want you now to realize, because it is an easy fix, is the following. As x approaches 0, think about it. What is 5x approaching? If x is going to 0, imagine you're multiplying 5 times 0.001, 5 times 0.000001, 5 times 0.0000001. 5x is also approaching 0. So if x is approaching 0, 5x is approaching 0. So you know what? There is no harm if I quickly change this to 5x. Because then the limit is still as 5x approaches 0. The variable, now your new variable, 5x, is also approaching 0. So you're not changing the neighborhood. 5x is also approaching 0, like x is approaching 0. And now you have a perfect match. So now you know indeed that this limit right here is going to be equal to 1. So you're going to have 5/3 times 1. That's going to give you 5/3 as the value of the limit. Okay. So I know that this part over here, this adjustment of the variable, is what sometimes generates confusions with students, but there's nothing to be confused about. What is really happening is making sure that we're not changing the neighborhood. X is approaching zero, right? We're approaching zero from the left and from the right. And if we are now considering 5x, you can think of 5x as your new variable. 5x is like you. We want to make sure that even here, this new variable, 5x, is approaching zero because what we want to preserve is the neighborhood. We still want to be in the neighborhood around zero. And it was really easy to realize that the neighborhood was not going to be changed because as x approaches zero, as x is getting very, very small, then we notice that multiplying the variable x by 5, so 5x, doesn't really change the outcome. 5x also approaches 0. So this allowed us to go back under the limit and to adjust the x by multiplying it by 5. So here above, if x goes to 0, 5x goes to 0. And what was really nice about that is that now we have a perfect match and we are able to use this result right here, that the limit as 5x goes to 0 of sine of 5x over 5x, that entire limit is equal to 1. And then when we multiply by 5/3, we get 5/3 as the value of the limit. Let's tackle example B. Very similar to A, but it has a twist. But it will encourage us again to apply the same skills as in the previous example. We have to find the limit as x approaches 0 of sine of 3x over sine of 7x. And I'm going to ask you again to remember the important result that I ask you not to ever forget. We want to remember that the limit as u approaches 0 of sine u over u is equal to 1, or the reciprocal, the limit as u goes to 0 of u over sine u is equal to 1. And I want to emphasize here again how we have to have a perfect match of the variable 3 times in this expression for this to be equal to 1. U has to match with u inside of sine and has to match with u under the limit. So u, and u. Let's go ahead and keep that in mind and begin our analysis. So here, I'm going to start by taking the limit as x goes to 0. And if you notice immediately, I have sine of 3x over sine of 7x. Unfortunately, 3x doesn't match with 7x. So I have a little bit of work here to do. I'm going to start by separating the numerator and denominator. I'm going to have sine of 3x times 1 over, one second, let me put times and let me give myself a bit more space, 1 over the sine of 7x. Okay, notice how I haven't changed anything, just the reorganization. Now what I'm going to do is the following. The goal here is to end up with an expression like this because I know that this limit goes to 1. I already know this. This is a tool and I want to use my tool. So here I have sine of 3x. That means that I'm going to have to multiply top and bottom here by 3x. So doing that, we're going to have times 3x over 3x. And for this factor, I would love to have in the numerator 7x. So I will multiply this by 7x divided by 7x. Now, let's see. I'm going to reorganize again. Some things I want to keep inside of the limit. Some things that I don't need, are going to come outside of the limit notation. So this 3x, I want to keep within the limit. Then I'm going to have a 3x bouncing around, And the same thing over here, this 7x, I don't really need it. What I really want is the 7x in the numerator. So look at this. I'm going to keep the limit as x goes to 0 of sine 3x divided by, and this 3x right now, I'm going to circle it in green. I want it here under sine of 3x. So I'm going to have over here 3x. Now, this 3x for now, I'm going to leave it here if you don't mind. I'm going to write it as 3x right here. And then moving on to the next one, I'm going to have 1. Actually, no, let me undo this. I am going to have division here, sine of 7x, and then this 7x, I want it here above in the numerator, so I'm going to have 7x, and this 7x in the denominator, I'm going to go ahead and bring it to join 3x. So I'm going to have over here divided by 7x. And again, all of this is right here. So please notice, you can even pause the video right now. This is a good place to pause for you to really make sure that you convince yourself that all of these components are in here, just reorganized slightly. This 3x was brought under, this 3x was left over here, this 7x was brought above, you can see it here, and this 7x joined 3x in the middle. Now, notice how these x and x cancel out. That means that this 3 over 7 is now a coefficient. X is canceled. So if there's no x anymore, 3 over 7 can come in front of the limit in my next step. So in my next step, I am going to have 3 over 7, the limit as x approaches 0, of sine of 3x divided by 3x times 7x divided by the sine of 7x. And pretty much, if you notice, this is already looking a lot like sine u over u. This is looking a lot like u over sine u. All that I have to do now is to apply the limit to this expression and to this expression right here. So then I am going to do that as 3/7, and then over here, brackets, I'm going to have sine of 3x divided by 3x, and this will be the limit, but now I am going to make my adjustment. Notice over here, as x goes to 0, 3x goes to 0. Please try to remember that. If x is approaching 0, 3x is also approaching 0. Similarly, 7x is approaching 0. So now I can change this variable x to 3x approaching 0, close brackets, times, same thing over here, the limit, but now I'm going to say 7x because I want to have a match with 7x, and then 7x divided by the sine of 7x. And I now know that this limit is equal to 1 and this limit is equal to 1. So given that, I can write 3 over 7 times 1 times 1, 3 over 7 is the value of the limit. Here we have another limit, the limit as h goes to 0 of h squared over sine squared h. And again, I'm going to put my reminder here of what we need to always keep in mind. right here, we want to keep in mind that the limit as u goes to 0 of sine u over u is equal to 1, and the limit of the reciprocal is also equal to 1. We have to keep that in mind. These are our tools, and we want to be able to utilize the tools whenever possible. So in order to do this, I am going to start again by reorganizing my expression. I have h squared over sine squared h. So let me rewrite it like this. H times h over sine h times sine h. And because this is multiplication, I can rewrite it as h divided by sine h times h divided by sine h. And then pretty much this limit here, it's already looking a lot like this one. So that means that I can apply my properties of limit. I can rewrite this with the limit as h goes to 0 applied to each factor. So this will be the limit as h goes to 0 of h over the sine of h. And then over here times the limit as h goes to 0 of h over sine h. I don't have to adjust the neighborhood, the variable under the limit, because now everything is just h, and I already have h. So no adjustment is necessary there. And I already know that this limit is equal to 1 and this limit is equal to 1 as well. So we're going to have 1 times 1, and that will give us 1 as the value of the limit. Last problem, we have to find the limit as t goes to 0 of cosine of t minus cosine squared t divided by t. I noticed that there isn't a single sign. It's interesting. So maybe we're not going to use the first result. Maybe we're going to use the second result that we learned about a limit involving cosine. But first, what I will do here as I begin my analysis is to factor this cosine out. I noticed that I have a cosine of t as a factor and then another one over here. So why not factor it out and see exactly how to proceed after that? So doing that, we're going to have the limit as t approaches 0. Cosine of t is going to come out. And then we're going to have 1 minus cosine of t, all this divided by t. Then I want you to notice that indeed we are going to end up dealing with this result right here. This was the second part of our discussion. Remember, we proved this already. We proved that the limit as u goes to 0 of cosine of u minus 1 over u is equal to 0. And I already see this fraction here on the left. So what I am going to do is a separation of factors. I will take the limit as t approaches 0 of cosine of t times 1 minus cosine t, but I want this expression to match this numerator here. And in here I have cosine of u minus 1. Well, that's an easy fix because all that I have to do is to factor a negative out. So I'm going to have here minus cosine of t minus 1 divided by t. And that becomes my expression. Similarly, now I know, just as we did numerous times in the previous examples, now I can take the limit and apply it to each factor. And I can do that because cosine of t as a function is continuous, so it has a limit at 0. And then this limit at 0 exists, right? This limit is exactly this one right here. So by properties of limits studied in section 2.3, I can apply the limit to each expression. So this will be the limit as t approaches 0 of the cosine of t that's the first limit, times, I'm going to put the minus in front of the limit. So the limit as t approaches 0 of cosine of t minus 1 divided by t. And the first limit, as t approaches 0 of cosine of t, that will just be equal to cosine of 0. That's a straight substitution. So here, cosine of 0. And then this limit right here that I am circling in green, that limit is this one here. So that is going to be equal to 0. So we're going to have times negative 0, 0. The cosine of 0 is 1, but anything times 0 is going to give us 0. So 0 is the value of that limit.